we would like to acknowledge and pay respects to First Nations people here in Perth. That would be the Whadjuk Noongar people, but also across Australia and across the world, and paying respect to their elders, past, present, and emerging. With that, we are on to day 4 of our P'Con conference, and we have another great lineup. It's the middle of the night, or near middle of the night, for our 2 speakers today, evening, middle of the night. So we do appreciate you coming on board. Maciej, over to you.
Yes, thank you. Thank you so much. And thank you to both Sunita and Maicon for agreeing to spend this evening and early morning with us. Today, the 4th day of P'Con conference, we will be looking at various experiences related to porting applications to GPUs and optimizing these applications on GPUs. We have a couple of talks and a panel later during the day, but I will start with welcoming and an introduction of Professor Sunita Chandrasekaran from University of Delaware. So Sunita is an associate professor with the Department of Computer and Information Sciences at the University of Delaware in USA, but she's also a computational scientist with Brookhaven National Laboratory, and she's also currently the PI for the ECP, so exascale compute project SOLVI, and Oak Ridge Research National Lab's CAR projects, among others. And today, Sunita will be giving a talk on preparing the software stack for next generation computing systems. Sunita, the stage is yours.
Thank you very much. Let me go ahead and share my screen and do this right. Okay. Does that look okay?
Yeah, that's looking great.
All right, thank you. So thank you very much, Pawsey Supercomputing Center, Maciej, for inviting me to this wonderful session of yours. I've been following on Twitter the different talks and things you folks have been posting. So glad to be here. Thank you for having me. So my talk is going to be on experience with porting and scaling codes on AMD GPUs, but we will also go through the process of where we are and where we want to be and all those things. And yes, it's 8:38 p.m. on the Wednesday, still here. So good morning to you all. Greetings, wherever you are. Thank you for joining. So I have 2 projects that I wanted to talk to you about. The first one is the exascale computing project, SOLVE, which stands for Scaling OpenMP Programming Model with LLVM for exascale performance and portability. And the other project is CAR, which is again Oak Ridge's project, like NERSC, NESAP, or again a project which is basically the goal being how do you prep applications for the next generation supercomputing system. So we'll go through these, and I plan to be able to share as much as I can. There is a lot of NDA involved, so I wanted to be a little careful of what I cannot share. But the CAR project is much more easy, more open than the exascale project itself. Anyhow, so the first project, exascale project, is the goal there is to develop, create LLVM, OpenMP, GPU offloading implementations, and help port OpenMP as well as OpenACC applications to exascale platforms. In the US here, obviously, we are looking forward to using Frontier very soon. So stepping through the project itself, we are a very big team, and I became the lead of this project 4 months ago, literally in September. So I'm still new to the whole thing and still trying to understand where is this headed, what is the project about, but it's been very dense with respect to so many sub-projects within the team, steep learning curve, and tons of work on different aspects. And I will tell you in a minute, the different pieces of the project. But my main co-PIs are Johannes Joffer from Argonne National Lab, and this is in Illinois in the US, David Bernhold, Oak Ridge National Lab, Branis Sapinski, Lawrence Livermore National Lab, and Vivek Sarkar from Georgia Tech. Besides that, number of students, PhD students, undergraduate students, grad students from my own group in the University of Delaware. And by the way, Delaware is in the East Coast, a few hours drive, probably 5 to 6 hours drive from New York. So literally on the East Coast, hugging close to Philadelphia, Maryland, and the other states around Delaware. So literally the tip in the ocean. So it's a large project, lots of stakeholders, lots of different pieces to the puzzle. So the different pieces to the puzzle itself is basically the very first goal, right? The very first piece of the whole project is to be able to help ECP AD teams. When I say AD, I mean application developers. These several acronyms, trust me, it took me months to learn 3-letter, 4-letter, 5-letter, 6-letter acronyms, right? And everybody talks in jargons. So it took me a while. So AD team is application developer. So the goal of Solve is to engage with those ECP AD teams, application teams, and help them, support them, assist them in moving their applications from whichever system they've been targeting to the exascale frontier system. And it's not just frontier, could be Aurora or Polaris in Oregon National Lab, basically the next generation supercomputing system. And Solve's goal goes also beyond ECP projects. We also solicit, or we also work with non-ECP AD teams as well, basically whoever is interested to use OpenMP, OpenACC implementations for their code. So the goal of Solve is to intensely engage with ECP application teams and help port those applications onto the next generation systems. And in that context, when you work with those ECP AD teams, they tell you their requirements, the user needs. And our job is also to go back to the OpenMP specification folks and tell them that, ABC application, this computational fluid dynamics application require XYZ features. And those features, we need prototype implementations of those features, and then they get ratified into the specification itself. So many pieces to the puzzle, but the goal is to be able to work with the application and understand what the requirements are instead of, just creating implementations after implementations. And in that context, we work with the AD teams, try to understand their proxy applications, mini applications, which are a tad bit easier than this humongous, real code. When you work with proxy mini applications, you can dig deeper, right? And you're able to solve bugs a tad bit easier than the main applications itself. Then another sub-project also proposes OpenMP extension, which is the part where people work with the OpenMP specification. Then enhancing LLVM compiler implementations for OpenMP, which means implementing new features and parallelism-aware optimizations and so on. There is also a runtime piece, Bolt runtime, which is part of Oregon National Lab, and Bolt's integration to MPI, Bolt's integration to the LLVM runtime as well. And the last but not the least, a very critical piece of the project, and this is the piece that I can tell you more about, is the validation verification test suite. There, the idea is to create functional test cases covering OpenMP specification 4.5 onwards, so 5.0, 5.1, 5.2 was ratified in November 2021 at the Supercomputing Conference. So writing test cases and stress testing them against any existing OpenMP applications and any existing exascale testbeds. So these are some of the bigger pieces. Obviously, as you dig deeper, each of these sub-projects have multiple pieces associated to it. This is a grand overview of the ongoing LLVM of OpenMP offloading implementations, where we see a range of potential implementations, starting from LLVM 11 and right now ongoing LLVM 14. And this is the team that not only works with their Solve hat on, they also work closely with the LLVM open source consortium, in the sense there are tests that we write, which is integrated into the, the bigger piece of the LLVM project itself, and vice versa. So if we create a prototype implementation, it's also part of the LLVM main trunk, and as well as the, Solve project. So PragmaOMP parallel, you might find the little code snippet there very familiar, where there's parallel offloading, portable OpenMP device runtime, map functions, and SPMD, the SPMD is for example, is some of the newer features into LLVM 13. And the one that is ongoing, a PR and pull requests, and something which is being reviewed as we speak, is the barrier elimination. So there are multiple pieces, and I've put 2 publications in the footer. These are ICPP 2021 workshop, I believe. The second one is a workshop. Another one is the IWOMP 2021 paper. So these have more in-depth details of the way these prototype implementations were created, tested, and eventually also utilized within the ECP applications itself. So to give you an idea, of the kind of applications we deal with, some of them are very core, ECP 80 teams. The one on the right-hand side, the green box, these are also CAR applications. Now, CAR stands for Center for Accelerated Application Readiness, which is a program part of the Oak Ridge National Lab, where the goal is to prep a cherry-picked handful of applications, groom them to be ready for exascale computing platforms. So obviously there are programming models like OpenMP and OpenACC involved. These mini apps are also associated to the main applications there. So obviously, first up, we started to work with mini applications to understand the requirements of offloading features, right? Mini sweep is something which my group has worked on very heavily. The code itself is from Oak Ridge National Lab. Initially, there was an OpenMP 3.1 port only on the host. Then one of my PhD students wrote an OpenACC version of Minisweep. We got performances quite close to CUDA, which is not easy, right? Because CUDA is a low-level programming model. And then Oak Ridge folks took Minisweep and created an OpenMP 4.5, 5.0 offloading implementation. And then these work have been going on over the past several years. And this is just one example. Similarly, each code have their own little proxy mini app. And Solve's aim is also to be able to find out what are the requirements and how do you port these mini applications, and hence the bigger apps. Then we are also involved with working with libraries like Slate, as well as C++, abstraction libraries, Cocos and Raja, where the idea is to, provide backends to Cocos and Raja, because some applications are very C++ intensive and they must be written in Cocos. Cocos themselves have multiple backends, you might be aware of, one of them being OpenMP. So Solve's idea is also to work with the Cocos team, which is its own ECP project, but enhance the OpenMP portion of their backend so that C++ AD teams are able to use OpenMP as their backend and target the different applications. So this is just an idea, and the progress that has happened with the ECP applications, and this is the lots of them are NDA info, so I don't have a specific slide to it. But what we have been doing is in the past couple of years, right from LLVM 11 to LLVM 13, which is the ongoing version, there have been several loop optimization, transformation, several optimizations that have been incorporated within LLVM itself in a way that porting all these are getting us a tad bit close to CUDA performance, which is the goal. We do want to get close to native kernels as much as possible. But as you can imagine, it is not easy because Solve team is not that big a team to be able to work hands-on with each of these AD teams, right? So we have been working towards, short of personnel, resources, bandwidth, time limit, because one thing is to work with mini applications, which, students might be able to handle. The other thing is to work with a 10x bigger version of these mini applications, right? The QMC pack, QCD, games is a Fortran application, Exastar, XGC, these are beasts, these are massive applications. So you need multiple software developers, application developers who can work together and go piece by piece by piece, right? From profiling and understanding where the bottlenecks are, and then, first create a prototype implementation on offloading and then optimize them, and then crunch performance to get close to native CUDA kernels. So this is where our current ECP solve struggles or challenges are, which we are trying to figure out, how to overcome. Because we get close to frontier, these applications need to be ready, right? And there is lots of work yet to be done. And another challenge we have been facing is Summit is the second fastest supercomputer housed in Oak Ridge National Lab, and Summit is IBM and NVIDIA system. Frontier is an AMD system. They are apples and oranges, right? So the code that is, for example, QMC pack that ran on Summit is not going to, run just like that on Frontier, right? There is going to be a lot of background effort in order to port QMC pack that has used, Summit relevant packages, and how do you migrate that to Frontier? So here is where the OpenMP offloading implementation's robustness, portability comes into place. So that leads us to a sub-project of Solve, which is open source. So I can, talk about this without any reservations. So this is a validation verification test suite project, and the last bullet you see is the site, the website to the VNV project, and there's GitHub. The tests are completely open source. You're welcome to contribute. And so going to the top of the slide once again. The validation verification test suite goal is to create feature tests, functional tests. We haven't much done orphan tests yet, but multiple pragmas in the same code kind of test, but it's more like a feature functional test, where the idea is to look at the OpenMP specification, understand the specification, create a functional test, right? And this stresses out on different compilers on different systems, and see if the test is correctly written, if the compiler is correctly functioning as it's supposed to be, and so on and so forth. And in the same process, in the same sub-project, we have also been extracting OpenMP application kernels from these large proxy mini applications to check implementation's conformance to the OpenMP specification. So here is where we have a ton of challenges, where we write a test case and it might be, passing an IBM Excel compiler, but it might fail a GNU OpenMP compiler. So where is the problem, right? Is the test written correctly, or the compiler is at fault, or did we misinterpret the OpenMP specification itself? All these could be part of the puzzle. And this is what takes up a lot of time. And we are a team of 2-3 scientists from Oak Ridge National Lab, and 3 of my students from UD who have been working on this since 2017, right from OpenMP 4.5, and now we are moving on to 5.1 specification. The providing quantitative analysis of OpenMP readiness on ECP platforms. At the moment, we have been using ECP testbeds, which includes Spec in Oak Ridge National Lab, and a couple of testbeds in Argonne National Lab, as well as Perlmutter in NERSC, Lawrence Berkeley National Lab. The tests highlight ambiguities in the OpenMP specification. So as soon as we come across, misunderstanding of the specification, we go to the OpenMP ARB and try and tell them that, look, this is the issue. So then, people discuss and see if they have to go fix the specification definition of a particular feature, so on and so forth. So we have a structure of how the test should be written, because imagine several people contributing to the test suite, which is great, but you don't want to lose the way the test should be written, because it's all integrated into this infrastructure. The features, the compiler versions are up to date as of, I guess, last month, November. So these IBM is on Summit, GNU compiler is on Summit as well, NVIDIA and LLVM compiler all on Summit platform. Cray, CCE, Cray's LLVM backend, AMD Clang backend is a Clang frontend, and LLVM backend is all on Spec, which is the exascale testbed at Oak Ridge National Lab. And the website in the last bullet has the tests, the results. So if you go to that particular website, we have a couple of machines, C, C++, Fortran, and then you can check the boxes and it would list the tests that is written. So this is an idea of the validation verification results itself. So what you see on the y-axis is the number of tests that have passed and number of tests that have failed. The blue bar indicates the tests that have passed, and the orange one indicates the test that didn't pass. And on the x-axis are your compilers, including Fortran XLF, that's a Fortran compiler, IBM, and these are C++ compiler. This is the GNU Fortran, GNU C++, and you can also see how the versions, progressively, how you have been testing the different versions. And then comes the Clang compilers, equally important, followed by Cray Fortran compilers, and so on and so forth. Right now we are at ROCm for CC++ 4.3. So what we have noticed is if we go back and test a few versions, earlier few versions till date, we can see that more tests pass, which is good, right? Because the compilers are being updated and the bugs are being fixed. But you can imagine the process, right? So we come across a bug, we have to report it to the vendor. The vendor needs to, put this in some file system or in some bug tracking system, Redmine, or we have some pages called Confluence, Jira tickets. It goes up there. And once the vendor fixes the particular bug that was indicated by the VNV, we need to know that the bug is fixed. So we need to get the next version, test it again, make sure the bug is taken care of. Why does this matter? Because we have all the application developer teams using all of these compiler versions, right? So in the event QMC pack, which is thousands and thousands of lines of code and multiple functions, multiple kernels, use OpenMP offloading and they encounter a particular failure, then we get them to check the VNV and see that, oh, is it failing here as well? Then we know that it's a common bug, and we know that this is a performant critical feature that the AD teams are requiring to use, which means we'll have to elevate that to the vendor and say that, look, among the 10 bugs we got you, this is a particular bug that more than one AD team have been encountering. That needs to be fixed. Else the AD teams in the solve liaison create workarounds. Now that's not a permanent solution, right? So these are a bunch of communication challenges, and I'm bringing up all this because I'm sure at Pawsey, Supercomputing Center, you have all these large AD teams, and you'll have to work with the vendors. So multiple stakeholders, so application developers, vendors, the software developers, and the facilities, and they all have to come together in order for one application to work successfully. And the difference that I'm seeing is the next project I'm going to tell you about is the CAR project, which is one application, versus ECP Solve, which is involved in more than 8 to 9 large applications. So accordingly, the challenges are blowing up. And that's part of the fun part of ECP Solve. So this is the exascale computing project itself. Thank you to DOE for getting us the resources and all sorts of things for us to be working on this so closely over the past couple of years now. The next project that I wanted to tell you about, and this is something that we have been working on since 2019 when the world was still normal. So this kicked off in October 2019, and this project is called CAR, Center for Accelerated Application Readiness. So across the United States, Oak Ridge National Lab selected, I believe, 8 application teams, and our application team called P'Con GPU is one of them. PIC stands for particle in cell on GPU. The fun part of me as a computer scientist working with physicists is I get these cool images. Isn't that wonderful? So this is a P'Con GPU particle in cell image from Felix Meyer and Richard Posch at 8ZDR, which is Helmholtz Zentrum Dresden-Rossendorf facility, a national lab in Germany. And the application is laser wake field simulation video, and this is using Summit and 48 volt 100 And Isec is the visualization plugin that delivers, these kind of beautiful images, and I have more coming. The goal of CAR itself is an application that performed X seconds or whatever, or the performance metric. In our case, it is Terra updates per second. Our goal is to make it go 4x faster, right? From summit to frontier. That's the goal set. And there are metrics that we have to follow. So we first ran P'Con GPU on summit in November 2019. And next we need to run P'Con GPU, the same application, the same case study on frontier and see if we got 4x speed up. So that's the goal. Frontier is EPYC CPU, AMD CPU, and AMD MI200 250X. This is, I guess, public info as of November 1st or 2nd week. And Frontier has approximately so much peak performance. So this is another big project where my team is across the little pond. So it's me and my PhD student and all the Center of Excellence vendors in the United States. And the rest of the team you see, most of them are in Germany. So communication is interesting, time zone, number of hours difference. So lots of Slack chat and lots of Zoom calls. And we have been functioning pretty well, I should say, even prior to COVID, because we have been doing this even before COVID, lots of offline discussions and then online phone calls to figure out, what's going on with the project. So my core collaborators, Guido Jutland, Michael Busman, David Rogers is from Oak Ridge National Lab, who is our CAR liaison from Oak Ridge National Lab. And Alex and Thomas, these are all key players, Rene and Sergey, on the software as well as the application development. And acknowledgement goes to Kasus, this is a Center for Advanced Systems Understanding, who is funding my PhD student on this project. And I'll also show you results from Jules at ULISH Supercomputing Center. So thank you for giving us those core hours. And the HPE AMD Center of Excellence, they call themselves COE, that have been helping us to get our application on board with the exascale testbeds. And last but not the least, of course, many thanks to OLCF, Oak Ridge Leadership Computing Facility. All right, so while I play this video, what I would like you to do is for 10 seconds, if you can, I want you to close your eyes. And I'm going to take you through a journey before I explain the physics, because this is how I learned it. And it took me months to understand what is the physics behind particle and cell, right? Because I'm a computer scientist, I'm not a physicist. So what I would like you to do is close your eyes, be patient, walk with me here, and imagine that you are in a lake. It's beautiful weather in Australia here. So imagine you are in a lake and imagine you have a cocktail and you're enjoying the weather. And I agree, it's 43 centigrade, but imagine it's beautiful weather. And imagine that there's a boat cruising through the water and it is forming waves, water oscillation, right? Then, so you are sitting by a lake, you're sipping some cocktail and you see a boat cruising by. Now, imagine you have surfers jumping into this wave, riding with the wave. They will get accelerated because of the wave caused by the boat that's cruising along. Now you can open your eyes because I'm going to play this video, which is what P'Con GPU is all about. So what you're seeing here is a gas chamber, a plasma gas chamber. And what is tearing through is the laser pulse. So that's the boat. Plasma gas chamber is your lake. This laser pulse is displacing electrons into this entire plasma channel. And it is creating a wake, which is like your water oscillations. And thus, this is creating positive, negative charged regions, which is accelerating the electrons to achieve these high energy electron volt particles, which is what P'Con GPU is all about. So we want to create this high energy particle accelerator, which is the goal of P'Con GPU. So how do we do it? We are at giga electron volt. We would like to reach to tera electron volt, although the physicists would correct me that it is not possible so quickly. But with Frontier and the next generation systems, that is our goal. How do we get to that high electron laser plasma accelerator? That's P'Con GPU. Thank you for walking with me here because this is how I learned to describe the video. So the impact of P'Con GPU itself is more than material, soft matter. It is also an important application in bioinformatics, where we have those cancerous cells, for example, that the laser pulse could target, but at the same time, the laser pulse could also target healthy cells, which is where we get lots of these side effects. So how to work around this, right? How do you target just the cancerous cells and not land up with so much of side effects because you don't have that accurate high electron voltage laser pulse? So radiation therapy, dense matter, soft materials are all some of the applications that P'Con GPU can impact. So coming back to CAR's goal, there is something called a figure of merit, which all of us were asked to follow. So figure of merit is, that's the definition for P'Con GPU, right? It could be different for different applications. For us, we calculate 90% particle updates, 10% cell updates by second. We get the form metric. So form metric is 1 on Summit. We got to get 4x of that on Frontier. So that's the goal. So P'Con GPU, it's not a million-line code project. You know, it's about, I would say, 50,000, 80,000 lines of code for project. And P'Con GPU has run on Titan, which was the other supercomputer back in 2012 in Oak Ridge National Lab. And they had, I believe, the first GPU-based system, K20, Kepler 20. Then P'Con GPU has run on Summit. P'Con GPU was also a finalist for ACM Gordon Bell in 2013 after running on Titan. So they can run on, P'Con GPU can run on Titan, can run on Summit. So you would think that it should be straightforward to get this to run on Frontier, right? Definitely not. So there are multiple challenges, as you can imagine, with the size and the intensity of the code itself. But before we get there, I wanted to draw your attention to your left-hand side figure, which is yet again a beautiful image created by Benjamin Hernandez from Oak Ridge National Lab, laser Wakefield accelerator simulation using Summit's 8 nodes with 2 billion particles and using Isec plugin, using the Slate environment from OLCF. So multiple challenges. There is performance challenge, portability challenge, programmability challenge, scalability, I/O, visualization, and the entire workflow. So to target the software programmatic challenges, what we use is a C++ programming language called a programming or abstraction library called Alpaca. So Cocos and Raja, if you've heard of those, which are US-based C++ abstraction library, similar to that is Alpaca. Quite similar, yet there are differences. Alpaca is the European version of C++ abstraction library, but the goal, as you can see, multiple targets, right? So we can use Alpaca to target AMD, NVIDIA, HIP, which is part of AMD, of course, CUDA backends, OpenMP host 3.0, OpenMP 4.0, 4.5, 5.1, and so on and so forth for offloading, SYCL, as well as OpenACC. And there are papers, and it's completely open source. CAR code and the software, everything is open source. So you can take a look at any of the pieces. It's C++ 14. And earlier this year, there was a release of Alpaca with OpenMP 5 target offload as well as OpenACC. And HIP backend is more stable and supports, this is Alpaca's HIP backend, more stable and supports HIP 3.5. HIP 3.5 is similar to ROCm 3.5. So if you have a ROCm 4.3 from AMD, which is the most, 4.5 is the most latest version, Alpaca would be compatible with that. So, so let me show you some results, right? So some of our experimental setup is Summit, Jules, Spec, which is the exascale testbed, and the software packages themselves are Alpaca, CUDA 11.1 through 11.3, and the AMD until 4.3. We haven't used 4.5, run into issues, but that should be the next version we would try, as well as OpenMP offload compilers and OpenACC. The other tools that we have used to profile and understand the performance analysis of P'Con GPU itself include NVIDIA's NVProf, which was still a tool back in 2019, early 2020. And now, as you know, the NVIDIA switched to Insight Compute and Insight Systems. I still wish we all could use NVProf because I think I like NVProf tool much better than Compute and Insight Systems. And then we also used AMD RockProf. So yeah, some of the benchmarks, GPU membench, that is to assess the on-chip GPU memory bandwidth, and Babel stream is to measure the memory transfer to and from global device memory CPU. So you might be familiar with this. I wanted to just jog our memories a bit for, because some of the plots are based off of roofline models, where on the right-hand side, you basically have an y-axis with gigaflops per second, x-axis is the arithmetic intensity, flops per byte, and depending on where your application is residing on this plot, you can determine if your application is compute bound, which means right under this horizontal bar, or if it's memory bound, if your little application lies under the slope. So so that's your roofline model, and it kind of gives you a good idea of where you are and where you want to be, and that this is the peak, right? Usually the bold horizontal line is the peak performance that a particular device can give you. And if you're hovering somewhere around at the bottom, then you know that you have much more to do to get close to as much as you can. And you don't want to be too much on the left-hand side of the slope, because this makes your code quite memory bound. And you want to be more compute bound, which means more operations, arithmetic intensity, and so on. So, right. So I'm jumping into the tool that we used for running our application on Spec, which is the exascale testbed, which has AMD MI100. Now, we do not yet have access to the systems with MI200 and 250X. I think we should by January. So all my results are from MI100. Now, the two kernels that you see are compute current and move and mark. The tool that we used to plot these is RockProf. Drop me an email, because I have much more to tell you than just telling you to use RockProf, because my PhD student, Matt Leinhauser, and this is an journal archive to be published in the TOPC journal. It's accepted, and it's an open source paper, so you can definitely take a look. This paper has many details on how we used RockProf for AMD MI100 and what were the challenges. The paper is 3 months old. At the same time, we talked to the AMD vendors on a monthly basis, and there are improvements to RockProf. So what you see in the paper is not super recent, but it's just 3 months old. So just putting it out there, because we were looking for flops metric, and we didn't have them in summer this year, but looks like the current RockProf versions do have metrics to measure floating point operations per second. So technically, you see a NVIDIA roofline model, right? So you'll have flops per byte. So this is the reason we could not plot flops per byte at the time of using AMD RockProf, August, September, or maybe over summer this year. So it is instructions per byte instead of flops per byte. But I guess with today's RockProf, you could plot flops per byte. And these are giga instructions per second and not, again, flops, right? So what you see here is HBM, high bandwidth memory of AMD MI100. Theoretical peak is so much. So this particular compute current kernel is hovering somewhere around here. So kind of compute bound, but the ideal scenario would be if this was, even in a better state. This is another kernel. So these kernels, we found out by profiling that there are a couple of compute intensive kernels as part of P'Con GPU, and those were the kernels we focused on. So again, so this is our peak, and that is our HBM. So this is kind of sort of more memory bound. So now you know where it lies and what we should do to make it do better. But some kernels are memory bound, so you cannot do too much about it. Though these are those type of kernels. And with NVIDIA Instinct Compute tool, yeah, so these are, I should have put this slide before the previous one, but this is the pies of the plot that tells us which different kernels to focus on. If you have used Instinct Compute, this might quickly occur to you what's going on, but if you haven't, this is NVIDIA's Instinct Compute tool. And this is the work we did first before going to RockProf. So we kind of figured, what RockProf plots would look like, because RockProf does not have a GUI like Instinct Compute, right? So the plot that you saw with the roofline model for RockProf is manually done using scripts. And those are the details I can give it to you if you're interested, and you can feel free to drop me a note. Everything is in a GitHub. So on the top, you see roofline plots for move and mark kernel. Single precision is your little L1, L2, flops, the red, the orange, and the blue ones. And all these different slope lines you see are the memory theoretical for L1, L2, and HBM. So, right, so arithmetic intensity for single precision as well as double precision. So usually when you compute your code, using the command line NCU target processes, and you have your rep file, compute.rep file, you invoke that nside compute, and nside compute gives you these plots. We did not create them. These were automatically generated, which NVProf did not give us. So that's pretty awesome. So there is a technical report that we created, and those links are here. I can share the slides with Maciej and Anne later on. So feel free to go through the technical report. So this is the Nside Compute tool, and the Nside Compute tool also gives you speed of light. So that's the very first box the Nside Compute tool gives you. Here it's streaming multiprocessors, telling you, it's compute intensive, but you can see the memory percentage is so long. Obviously, as we saw, move and mark kernel was memory bound, and that is what this particular box tells you. So these are nice plots that Nside Compute gives you. We also used Nside Systems, which tells us, where the hiccups are in the code, how it is not well balanced and all those things. That would be a different tool, Nside Systems, which is why I love NVProf, where all these things were sitting in one tool. Now we have to compile differently for you to use two different tools, which can be interesting, can be not. Okay, so let's look at some results. So what you see, new tweak. So tweak is a case study of P'Con GPU, and that is the case study with the form metric that we have been using for car code. So this is the figure of merit run on Summit, Joules, Spec, right? Summit is an Oak Ridge National Lab. Joules is Jülich Supercomputing Center in Germany. And then we have Spec, which is the AMD MI200 exascale testbed on Oak Ridge National Lab. So we're looking at two kernels, execution time, lower the better, giga instructions per second, instruction intensity, higher the better. So what we see for move and mark is these other numbers, right? So you definitely see Ampere 100 performing better, but that is not rocket science. I think this is a given. What we were a little optimistic to see that the MI100s were close to V100, could do better, but we are getting there. The same to do with compute current as well. Execution time, lower the better. So definitely A100 stole the show, not surprisingly. So giga instructions per second, higher the better. Here you see so much, but something very important to take away is it depends on how the tool is measuring, right? So giga instructions per second, higher the better. This is not really apples to apples comparison, which means 4.63 is not necessarily bad. The ROCprof giga instructions per second gives us accurate instructions of what we need. On the other side, Nside Compute tool and Nside Systems, they give us extra instructions. So I can't say it is quite inaccurate, but it gives us more instructions than need be, which is why you see a little higher number. Excuse me. Just looking at my notes real quick, if I missed something. Yeah, instruction type metrics that can be aggregated across all the compute instructions versus don't do the aggregation. So obviously the number of instructions go down. Instruction intensity, again, similar story. So here you see dashes because at the time of measurement, like I said, ROCprof did not give us flops, right? So, excuse me. So what you see for NVIDIA is 4.7 teraflops, FP32, FP64. I believe if we used ROCprof today on MI200, we will have these cells filled, and I'm looking forward to using it. Very similar to move and mark is also compute current, where compute current is not an FP64 kernel, which is why I've struck it off, but you do have FP32 teraflops, and those are the numbers. So we plan to keep adding to it. So there must be another column for 250, 250X, AMD GPUs as and when we get access to it. So I'll go a little faster. So this is Isec visualization plugin, and this is ROCm 4.3 AMD GPU and visualization. And this was a breakthrough for us because up until 2-3 months ago, Isec plugin and ROCm were not compatible, which means we couldn't visualize P'Con GPU on AMD GPUs, but now we can, which is pretty cool. This is weak scaling on Summit. This is as of, so this is weak scaling on Summit, scales pretty well, a little bit of, dips here and there. There were some MPI communication related issues. And this is also using half the Summit because that is what we had access to around summer. Summit was busy, so that's what we did. And the average was around 7.9 tera updates per second. When we ran the same tweak, the older version of tweak, unoptimized version of tweak, we had definitely a lower tera updates per second in 2019. So what we are seeing is 2019 tweak on Summit fetched so much versus June 2021 tweak fetched so much. But why is this important? Over the period of time, over the period of 2 years, 2019 to 2021, not only have the hardware improved, but the application also has been improved over the period of time, which is equally important, right? To get the right kind of performance you want. So as the COE, the Center of Excellence, AMD, HPE, Cray, tweak their hardware, we go to our corner and tweak our application, and both of them have to work in tandem. This is what I was talking about with respect to ECP applications. This is one application, one large team. ECP 80 teams are multiple teams, right? But imagine doing the full 9 yards of car code to the ECP 80 teams. It's a challenge when you have to get to the details. You need enough person power. I'm going to skip this because it's basically telling you that A100 is great, which I think we all know, Ampere 100, because these two columns are comparing Volt 100 and Ampere 100, and Ampere 100 obviously did great. And this was when we had access to Joules, which was until November 30th. So we were able to run on Joules. I think I'm coming close to an end. So correlations between Summit, Joules, and Spec basically are, the bottom line here is how you can have, and that's visualization. I'm going to let it run, sorry. So A100 definitely superior, V100, MI100 are neck to neck at par. OpenMP offloading implementations still have a lot of hiccups with P'Con GPU. Not surprised because C++ implementations are complicated. OpenACC also have bugs tickets that we have created for P'Con GPU. All these are work in progress. We hope to get OpenMP and OpenACC version of P'Con GPU running on Frontier soon. So I'm going to keep moving. And yes, this is thanks to the entire team for helping. These are all HPE and Cray and AMD folks who have been working with us. The one last thing I wanted to leave on the table, because I believe you are also in a big supercomputing center and you would be benefited from using benchmarking your code, because that can help you in many different ways. To that end, I wanted you to know about the Spec Standard Performance Evaluation Corporation HPC 2021 benchmark suite, which was released a couple of months ago. UD is part of Spec, so my group has been working with Spec over the past, I guess, 10 years now. This particular effort is 2 to 3 years, 3 years old, where we had solicited a lot of applications from the HPC community, close to 9 full and proxy applications ranging from CC++ Fortran with multiple workload, which means tiny is something that you could run on a decent desktop. Small is a little larger, medium even larger, and the large workload was still not large enough for machines like Summit, but at least you can see how it scales on such large systems. So Spec HPC 2021 benchmark suite is open for, and there is no charge for non-profit organizations. For profit organizations, there is a purchase you have to make, but the goal or how we used the ECP applications and car codes have used Spec HPC 2021 is to be able to stress test compilers. All of these different frameworks is what the Spec suite consists of. So MPI only, MPI OpenACC, MPI OpenMP host, MPI OpenMP offloading. And you get 9 different applications encompassing all these different 3 different languages and 4 different workloads. So you can stress test your machine. RWTH Aachen and TU Dresden cluster folks have found out bugs, faulty nodes as part of their clusters by using Spec HPC 2021, and they were able to isolate those nodes. These are the list of benchmarks as well as the contributors to the Spec HPC 2021 benchmark suite. That is my last slide. Yeah, so feel free to let me know of any questions. I'm sure there is quite a lot of them on Zoom chat, I guess.
Yes, yes. Thank you so much, Sunita. Great talk. And yeah, we have a couple of questions. So I'll read a couple of questions that we had on collected in the chat. Few of the first questions are actually related to the first part of your talk. So there is a question about the pass criteria for various OpenMP tests available in Solvi test and benchmarking suite. And the follow-up question was it only right solution, or do you use some minimal flops to be achieved? So basically performance-wise, or just a verification of...
Right. I believe this is for ECP.
This was for the ECP. Yeah.
Thanks, Sunita.
Yeah. Pass criteria is first up, the code has to run and be correct, right? So it has to validate, definitely. And then there is a performance goal in the sense that at the very least, you have to get a par to the native kernels. So correctness is the first criteria, followed by the application being able to run using more than one compiler implementation, right? So with OpenMP, you have IBM, Clang, AMD, GNU, Intel. So it's got to run with more than one compiler implementation and more than one platform. So in our case, it is Frontier testbed, Frontier itself, and Aurora in Oregon National Lab, whenever that is in place, as well as Perlmutter in NERSC. So Perlmutter is 800, Frontier is MI200 250X, and Aurora is technically supposed to be Intel GPUs. So that's the pass criteria.
Okay, thank you for that. And the second question was...
yeah, I'm reading it
okay.
from
I also, if you're fine, I will also read it loudly for the recordings. So you mentioned accelerated OpenMP performance with the goal of being close in performance to their native CUDA counterparts. For those applications you have been working with, how close to native CUDA performance have your team been able to reach? Within X% or within the same order of magnitude, etc.?
Yeah, thank you. Yes, that is a great question. Mini benchmarks like SU3 and XS Bench and RS Bench, these were at least at par. I can't say that the LLVM implementations were, 10x better than native kernels, right? Because if that was the case, then we would be in a very good shape. So they were at least at par, or maybe a 1x or 2x, but these are mini applications. We are in the phase of porting the real world applications where there is the, more of a challenge, right? Because these are massive codes. Sorry, one more comment is XS Bench, RS Bench. Toby, if you could drop me a note, I can send you the publications on it, because I think these papers are published, and that tells you a good idea of how close they are to native kernels.
Thank you, Sunita. And the next question was, do you keep OpenACC CUDA HIP equivalents to each test in order to also compare against? And that question, I think, is again from Alexis, and I think it might be, but Alexis, feel free to unmute yourself and ask it loudly. But I think that was in relation to the validation and verification tool.
Yeah, exactly. Yeah.
Yep. Okay.
Yeah.
OpenACC CUDA HIP equivalent to each test.
What I understood is the tests are for OpenMP offloading. And then so it's more related to compare performance against the other.
Oh, I think you mean performance benchmarking, right?
Yeah, well, I understand you are basically testing the OpenMP I don't know, directives to work well, but
Yeah.
also I guess you may be interested, besides working well, how well they behave against the other paradigms.
Oh, got you. Yeah. With the validation verification test suite, they're OpenMP offloading centric, but there is a performance benchmarking effort where, yes, with respect to at least those mini apps and proxy apps, the goal is to keep OpenMP offloading, equivalent, right? With CUDA, with HIP equivalent as well, OpenACC as well. So yeah, that is the goal, but I can't say that every proxy app has actually maintained it, right? Yeah.
Okay, thank you.
I think from my memory, when I was working with the verification and validation tool that you're developing, I remember that you also, at least in the first paper publication, you also had a performance reported for things like overhead of setting up the GPU offloading, memory copying from CPU to GPU memory, and so on and so on. Most of the tests are validation whether the specific pragma works with a given compiler, but you also have a way to record performance of setting up that offloading, right?
Correct. Yeah, that is correct. That is the creation of the OpenMP directives overhead itself. But actually, this is an excellent question, and I'm glad you're asking, because from the ECP solve standpoint, I think we have a lot more work to do with respect to creating that robust performance benchmarking suite, because that's what will tell us where we are, right? We don't quite have that robust. There are bits and pieces, different people in different labs working on it, but I think we need more of a centric one.
Okay, and the last question we have in the chat is related to programming models. I'll just mention that Sunita is also one of the organizers of workshops at SC, looking at various directive-based programming models and in general programming models for various GPUs. And this question is about Alpaca. So Marco is asking, have you got any idea of the current uptake and how many packages are currently adopting it and whether it's the popularity of it is growing? You also mentioned Raja and a couple of other packages. So like in the context of of other similar tools.
You're right, Alpaca, if you're asking of who else is using it, right? So this is often my question as well to HCDR. I believe there are multiple users, including CERN, from what I've heard, and other applications in Germany in general. It's a European-based tool, but CERN is the one that stood out and clearly I can remember. Other packages, especially for C++ abstraction library, honestly, I'm not aware of anything beyond Coco's, Raja, and Alpaca. They are the ones who come close.
Okay. Thank you so much, Sunita, again.